Hello everyone, I am Pushpita Chanda. I am a PhD student at IIT Delhi under IIT Delhi and University of Queensland joint PhD program. So I am the TA for this course, Applied Optics. So let's start with this session. So let's dive into the today's this week's not today's this week's module. So the week 3 actually comprise the module 3. In this week we will the professor has discussed about Huygens principle, concept of wavefront, and like polarization, uh, addition of the wave, not we should not say addition of the waves and the superposition of the waves and so on. So I'll first do some quick recap. So basically, before Huygens principle, simple people used to believe that uh, light Newton, what Newton proposed, that the light is like a luminous body which like emits a stream of tiny particles in all direction. So before Huygens particle, Newton gives this a simplest model of light, which is called corpuscular model of light. And this model says that the luminous body emits a stream of tiny particles in all directions. But this model cannot justify or explain reflection or refraction. So we needed another model. So Huygens proposed the principal or wave model in 1678. So basically, and then after that, like there are many scientists who propose different propose different theory about light. Young's they, Young's double slit interference is a very good experiment that can be explained on the basis of wave theory. Then Malus gave his polarization of light theory. Then Fresnel's came and he explained diffraction of phenomena. So, although these things, the Young's double slit experiment and Young's interference experiment, that happened much later than 1678. So, basically, after Huygens proposed the principle, all other things started to fall into place. So, basically, what is a wavefront? First, we want to know that what is the wavefront. So, wavefront is the locus of all the particles who are in the same phase. And professor has explained that in the class, that if like a small stone is thrown in the still water, we can see the ripples, and not and there is a circular ripples. So each ripple, at each ripple, all of the like water at that it is same phase in same phase. So wavefront is like that only. So basically, if we have a point source, we get wavefront like spherical. I am drawing a circular wavefront, but it's 2D. In 3D, we get a spherical wavefront, like from this point, every point is like if we say this is t is equal to t1, this radius would be vt1, and v is the velocity of the light in that medium. And if we get this way from a t is equal to t2, it would be vt2. So that's the thing. And now when we know that when the circle become much bigger, or sphere become much larger and larger, for a small part of that thing we can say it is a like plane wave. So at a very large distance, the radius of the sphere seems to like straight, and that's when we know we call it plane wave. Then similarly, if the source is like a straight line, then the wavefront is like, so basically the if the source is a straight line, so there is a particle who are emitting the light. So at time equal to t1, every wave will be at vt1 distance. So if that happens, you will see, or you can imagine, that the wavefront will be like symmetrical. So now move on to the, so, and I'm not writing because these are all in like in the slides. So basically, according to Huygens principle, each point of a wavefront is a source of secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. So basically, what I was talking about, that for each wavefront, this is source. Then again, there will be another. Say this is a wavefront, so there is a point on wavefront, and these points will act as the secondary source. So they will also try to propagate like this, and this wavelength, the envelope of this new wavelength will give you your next wavefront, and that's how uh, light moves in a medium according to Huygens principle. Yeah, and also there is a possibility of a back wavefront. Like if we add this wave, well, like envelope, we should get a back wavefront. But from the from many experiment, and also from many like what should I say? Many theory, we can say that the intensity of this back wavefront is so less that we absolutely deny the possibility of that back wavefront. Light always move ahead, not backwards. So we know the refraction condition n1 sin I equal to n2 sin R, right? So n1 or 1 n, what is that? That is basically c by p. Okay, so sin I by sin R is basically v1 by v2, right? And this is also equal to lambda 1 by lambda 2. So you will see that lambda 1 by v1 is equal to lambda 2 by v2. So this ratio remains same, and this ratio is nothing other than, or you can write it as v1 by lambda 1 and v2 by lambda 2, whatever you decide. So this looks great. So this ratio remains same, that is frequency, or f, remains same. So that means it, try to remember always that we are in a domain of linear optics. Here we don't assume that we can generate new frequencies, and like it's not that straightforward that we cannot join. So this part of optics, regarding linear optics, we can say that no new frequency gets generated. So always remember that in the reflection and refraction, even though the velocity changes, lambda changes, but never the frequency changes, that remains same. This comes from very basic um, assumption, not assumption, because uh, it is not assumption, it is actually kind of fact that in the reflection and refraction, no new frequency getting generated. To generate a new frequency, we need a like second order harmonic generation and something. So by that we get like other frequencies, and how we do those second order generation and all those things, and they are also we like we in use those material vision, we which shows wide difference effect. So in the polarization along the way, you get to know that there is a like ordinary wave and the extraordinary wave, and how they behave. So and the birefringes, like how they reflected and the exchanges. So using those materials, not only those materials, and there should be other, there should not should be, there is other materials. You can generate second harmonics, and when the second harmonics generates, then only the new frequency uh, got generated. Otherwise, in normal reflection and refraction, uh, frequency never changes, it remains the same. And the next one, this is the very like bare minimum that what we have seen, that the superposition of the waves and like then reflection and refraction. Now we need to now we will discuss some basic thing, that is superposition. So now we move to the next part discussed in the class, which is basically superposition of waves. So we know the wave equation is psi del x square, and this is 1D wave equation, t square del square psi del t square. For 3D, here we will get a y component, partial derivative with respect to y and partial derivative with respect to z. Also we can write it like this is the 3D wave equation. One wave square is psi del t square, and if psi I, like psi 1, psi 2, psi 3, psi 4, is the individual solution, then psi RT, superposition of all those psi, is also a solution for this wave equation. Now, this is same as the quantum mechanics. In quantum mechanics, you also write a wave equation, and that is also follows like the thing. So here, basically, we know we have arrived the conclusion that we are discussing the domain of optics where no new frequency generate. So here, when overlapping, we are discussing overlapping of waves that have same frequency. Okay, this is very important. So that can be done in three method, that is algebraic method, second the complex method, and that third the phase addition. So here in the class only the algebraic method has been discussed. So we know that harmonic waves can be written as form of like this, E0 sine omega t minus kx. Now with you can also write it as a E0 sine omega t minus kx minus epsilon. The epsilon is initial phase, and here for the simplicity we follow the notation E0 sine omega t plus alpha. Alpha is a function of x, so basically we said this is alpha. Alpha is basically minus kx plus epsilon, so this is a function of x and if psi 1. So if there is a two-wave E1 which is E0 1 sine omega t plus alpha 1 and E2 is E0 2 sine omega t plus alpha 2, the resultant disturbance became the E1 plus E2, which is E01 sine omega t plus alpha 1 plus E02 sine omega t plus alpha 2. So after all this calculation, you can write the resultant as E0 sine omega t plus alpha, as the frequency of both the disturbance, which is E1 and E2, is same, so the resultant frequency will be same. Alpha will change, and so the amplitude. So what would be the alpha? So there should be a relationship between the input of the we shouldn't say input, like the consecutive waves and the resultant waves. So E0 square is basically E01 square plus E02 square plus 2 E01 E02 cos alpha 2 minus alpha 1. Always remember this, and how this equation came, that has been discussed in the class thoroughly, and it is the relation between alpha 1 and alpha 2 and alpha, that is tan alpha is basically E01 sine alpha 1 plus E02 sine alpha 2, and that is E01 cos alpha 1 plus E02 cos alpha 2. This is the relation between E0 and E01, E02, and alpha 1 and alpha 2. So this term known as the interference term. So we know when two from our basic knowledge, when two waves like superpose, there we will get a interference fringe. In Young's double slit experiment also, we get a interference fringe, that is a maxima and then minima and so on. So like this. This is a maxima, this is minima, again maxima, minima, and so on and so forth. From interference, then there come like from diffraction and all those things. So this interference term 2 E01 E02 cos alpha 2 minus alpha 1, basically this one, alpha 2 minus alpha 1. So this actually defined, we will get whether maxima or minima. If delta is 0 plus minus 2 pi plus minus 4 pi or even multiple of pi, we will get maxima. And if delta is equal to 0 or not 0, plus minus pi plus minus 3 pi or odd multiple of pi, we get minima. So that's how it became. So we know delta is equal to alpha 2 minus alpha 1, so that is basically kx2 kx1 minus psi 1, So we can take common k is 2 pi by lambda x2 minus x1 plus epsilon 2 minus epsilon 1. So if they were initially in phase, then psi 2 minus psi 1 becomes 0. So delta remains only 2 pi by lambda x2 minus x1. So can also say it is 2 pi by lambda naught into n. So we know n is equal to c by v. V is equal to lambda. So for n naught, which is in the vacuum, first lambda is equal to c nu n. So c is constant, nu is constant. So lambda and n varies like this. So also we know lambda naught, which is the lambda wavelength in vacuum. So you can put the n value here or c by v value here, and which is n naught. So you can get the relation how we can write this lambda is equal to lambda naught by n. So here n basically n naught. X2 minus x1. So this is optical path difference. So x2 minus x1 is path difference only. When it is multiplied by the refractive index, it becomes optical path difference. And the phase difference is 2 pi by lambda into optical path difference. Then we dive into the concept of polarization. So we know light is an electromagnetic wave that has a E field, magnetic field, and a propagation vector. So they are all perpendicular to each other. So the polarization is basically the characteristic of light which is related to electric field vibration. Now we need to remember that we are considering isotropic media, and why isotropic media? Because there are different kind of medias which are anisotropic media, and on those medias we basically act as a birefringence that in isotropic media the polarization of light is same in all direction, but in that anisotropic media birefringence occur, and in some direction polarization is different. If polarization is different, the velocity of light and the refractive index of the light along those axes will be different. So more will be later in the course, or on the different course, that what is by refranges, what is like O ray, what is extraordinary ray or E ray, and all these things. So then an important concept is plane of vibration. So the plane of vibration consists electric field vector and k, a propagation vector in the direction of motion. So here the plane of vibration will be this, because direction of motion is in this direction. And now we'll discuss what is linear polarization. Basically, linear polarization is that if two orthogonal optical disturbance can be superimposed on each other, then the resultant is a line. Basically, uh, that line can be like this. Sorry. The line can be like this, or 45-degree, this, or this. Or literally this. They are all the example of linear polarization. So we consider two orthogonal optical disturbance, that Ex, Zt, or you can say that an optical disturbance is going like this. It has X component and Y component, or the optical disturbance is going moving in a right circular polarization. It or have x-axis and y-axis, and the initial phase difference between this x-axis and y-axis component uh, tell us that whether it is a RCP or right circular polarization or linear polarization and all. Uh, so you can say that if the two orthogonal optical disturbances have a certain initial phase, it gives a certain polarization of light for resultant, or you can see as that certain electric like electric field polarization can be like divided into two parts, an x-axis component and y-axis component, and uh, this polarization determine the initial phase difference between this x-axis and y-axis component. uh, you can see whatever seems to be easy for you. So here it is cos kz minus omega t, because uh, the direction of propagation in the z direction, and we are saying x component and y component of the equation v0y cos kz minus omega t plus epsilon. So like this. So if epsilon is 0 or multiple of m to pi, then Ez, which is the addition of this two, will be linearly polarized. And the angle, like here it is 45 degree, how much is the angle? The angle tan theta would be E0y by E0x. If the angle or initial phase difference is odd multiple of pi, then they are 180 degree out of phase, and then we get the opposite direction linear vibration. So for this case, the initial phase difference should be 2m plus 1 pi, and this is for this is 0 case, and this is 2m pi cases. For circular polarization, for circular polarization, if epsilon is minus pi by 2 plus 2m pi, where m is equal to 0 plus minus 1 plus minus 2 minus 3, and epsilon is minus pi by 2 or 3 pi by 2 and so on and so forth. Or sorry, this should be not 3 pi by 2, 5 pi, okay, also 3 pi by 2 and 5 pi by 2, and so on and so forth, minus 5 pi by 2 actually. Basically you put the values of m, so when m is equal to 0, this is minus pi by 2, when m is equal to 1, that is actually 3 pi by 2, when m is equal to minus 1, that is minus 5 pi by 2. For these values we are getting RCP, or light circularly polarized light. And So this is called rotating clockwise at an angular frequency omega as seen by observer towards whom the wave is moving. So if an observer is here and the wave is moving in this direction, the observer will see that this is moving, the point of the resultant electric field is moving the clockwise like motion. And for shell n is equal to pi by 2 plus 2m pi, where n is equal to 0 plus 1 plus 3. That means epsilon pi by 2 when n is equal to 0, then 5 pi by 2 minus 3 pi by 2. For these values, again when the light is moving toward the observer, the observer will see that the resultant electric field is moving with the angular frequency omega in anti-clockwise. And that is called left circularly polarized, or LCP. CP is right. Polarized. LCP is left circularly polarized. So, and then there comes a concept called electrically polarized light. So, elliptically polarized light is the most generalized form of the polarization. So, circularly polarized light and linearly polarized light are the special case of electrically polarized light. So basically this is it has a axis and B axis. So if A or B either become 0, it becomes a light basically. If A became 0, become 0, we get like this. If B become 0, we get like this. And if A is equal to B, then we get circle. So the basic equation or most general equation of electrically polarized light. Is Ey by E0y whole square plus Ex by E0x whole square minus 2 Ex by E0x Ey by E0y cos epsilon is equal to sine square epsilon. So here tan 2 alpha will become 2E0x 2E0y cos epsilon E0x whole square minus E0y whole square. If the principal axis of the ellipse is aligned with the coordinate axis, so alpha is the angle. Here, this is the alpha. If, for example, this is the ellipse and this is the axis A and this is B, alpha is basically this. So when alpha is equal to 0, that means epsilon is equal to plus minus pi by 2, plus minus 3 pi by 2, or plus minus 5 by 2. So we have seen that what will happen when alpha is equal to pi by 2 or minus pi by 2, we will get a circularly polarized light. And so the equation also becomes Ey square E0 y square plus Ex square E0 y square is equal to 1. So we get circular polarized light and the equation for circular polarized. And if epsilon is even multiple of pi, we are getting linear polarized light, and if it is odd multiple of it, then also linear polarized light. Okay. Now we discuss that how we get these polarization angles and so on and so forth. So how we get that by looking at the, so if ex is equal to a cos omega t and ey is equal to a sin omega t, so what will be the polarization thing? So basically in this scenario, how we get to know that what will be the like polarization, we just keep t is equal to 0 at, then ex is equal to a and ey is equal to 0. So ex is a and ey is 0. Well, that's good. At t is equal to pi by 2 omega, ex becomes 0 and ey is equal to a. So this, so this is our x-axis and this is y-axis. Then comes t is equal to pi omega, then ex became minus a and ey becomes 0. So that point is here. So basically it's moving like this. Then t is equal to 2 pi by, oh, first there is 3 pi by 2 omega, 3 pi by 2 omega, we get ex is equal to 0 and ey is equal to minus 1, which is here. Then at t is equal to 4 pi by 2 omega or 2 pi omega, then again we got ex is equal to a, ey is equal to 0. Similar thing happens at 4 pi by omega, 6 pi by omega, and so on and so forth. So you can see the tip of the electric field moves in an anti-clockwise direction. So you can say that it is a LCP. Okay. So same thing you can say that if in that case, if this is not a cos omega t and b is a sin omega t, instead of a that is a cos omega t and b sin omega t, you would get ellipse. So In ellipse, you will get LCP or LEP or REP, which is right ellipse, uh, right elliptically polarized light, and left elliptically polarized light. So we can say that it comes from Ex is equal to A cos omega t, and Ey is basically general from cos omega t minus theta. So if here theta is equal to, in that case, theta has become set 90 degree and A is equal to B. Okay. Now if A is equal to P and theta is equal to 3 pi by 2, then Ex is A cos omega t and Ey is basically minus A sine omega t. So for 3 pi by 2, we get, see here, 3 pi by 2, we get RCP. So at t is equal to 0, Ex is equal to A, Ey is equal to 0, and t is equal to pi by 2 omega, Ex is equal to, so Ey is equal to minus A. So here it is going, then will go there and go there. So this is going like this. So we can say this is RCP. And even when A is equal to P, but theta is not equal to n pi by 2, the electric field tip will electric field vector tip will rotate on the circumference of an ellipse. So if you consider that we have seen that linearly polarized light is basically 0 or m into 2n pi or 2m plus 1 pi. So that is basically a multiple of pi by 2. Then come circular polarized slide. That is also, this is basically we get pi by 2, 3 pi by 2, minus 5 pi by 2, and for left circular polarized slide, pi by 2, plus pi by 2, minus 3 pi by 2. So they are basically all the angles are multiple of pi by 2. If the angles are not in pi by 2 or multiple of pi by 2, for say pi by 3 or pi by 6, then even when the electric field amplitudes are in x component and y component are equal, it will not give a circle or linearly polarized line. They will give an ellipse. So we can see that an example. So we assume B is equal to A with theta is equal to pi by 3. Then Ex became A cos omega t, and Ey becomes A cos omega t minus pi by 3. So at t is equal to 0, again Ex is equal to A and Ey is half of A. So Ex will be A and Ey is A. This is X and this is Y. So it would be like this. Then at t is equal to pi 3 omega Ex. So we are taking t value like this, that the Ex and Ey value is easy to locate on the curve. We took such value that Ex becomes 0 or minus A. Here is also the same, that A or half of A, like this. So Ex became half of A and Ey is equal to A. So the next point is Ex half of, and Ey is A. Similarly, if t is equal to pi by 2 omega, then Ex becomes 0 and Ey becomes root. Ex becomes 0 and Ey becomes 3 by 2A. So this is 0, this is root 3 by 2A. Then the next point becomes Ex is minus Y minus A and minus half. So this became like this, and they are rotating in LEP. So T is equal to pi omega EX, basically minus A, and Dy is minus half of A, and so on forth. So that will rotate like this, and if P is equal to A and theta is equal to 2 pi by 3, then you will get a you will get like this, and this is also ellipse, which is basically a REP. So you take the value of like theta, so that we will get our REP or LEP. So even if, so let us summarize. If E0x and E0y is equal and theta is a multiple of m pi by 2, which is the even multiple of m or odd multiple of m, even for like multiple when it is 0 or 2m pi, you will get line. Same for pi, you will get line. For minus pi by 2 plus 2m pi, you will get RCP. For plus pi by 2 plus 2m pi, you will get LCP. So any of this like form is basically m pi by 2. So you will get some linearly polarized or circle polarized light. But if even when E0x is equal to 0y is theta is not equal to m pi by 2, say pi by 3, 2 pi by 3, and so on and so forth, we will get electrically polarized light. And also if E and also if E0x is not equal to E0y, then also we'll get a like electrically polarized light. So this is the summary basically. Now we will briefly discuss uh, Malus law. This law says that a Polaroid, first, what is a Polaroid that we need to discuss? Wait a second. So Polaroid is a plastic sheet which can align unpolarized light. That it's basically has a pass axis like this or this or this. Along this pass axis, that component of electric field only pass. So this is unpolarized light. Unpolarized light when it pass with when it pass through the polarizer, so unpolarized light when if there is unpolarized light after the polarizer is like this, if there is unpolarized light after the polarizer is like this and this one polarized light, we get the output like this. So Malus law says that we consider a Polaroid P1 which is a pass axis parallel to the x-axis. So here x-axis is in that direction, remember, and this is the z-axis. So the emergent wave will oscillate along the x-axis. Then if we consider that there is another Polaroid that is P2 whose pass axis is making an angle theta with the x-axis, then the intensity here would be I is equal to, if here is the intensity I naught, not here, actually here, I naught cos square theta. That is the Malus law. And theta is the angle between the axis of the light and actually vertical angle between the pass axis of the Polaroid and the light. So theta is the angle between lights polarization direction and polarizers transmission axis. So here was the I naught. I naught was the uh, intensity of the emergent like intensity of the emergent from the P1 when it became polarized. So always remember that. Now let us discuss a question. So always remember theta is the angle between this. Theta is the angle between the polarized lights direction, lights polarization direction. When we are talking about unpolarized light, we don't have a polarization direction. So Malus law only applied when there is a polarized light first, and then the angle is between the light's polarization direction and polarizer's transmission axis. The first question is polarization direction of the light, or you can see that polarization direction of light and polar. So when we are asking about unpolarized light that called I dash, then I naught would be I dash by half first. Then here is I will be I0 cos square theta. So when we put unpolarized light in front of a Polaroid, only half of them transmit. It is a well-known theory. Then then it's like the first polarization transmission axis is totally vertical or horizontal, it doesn't matter. The first light is unpolarized light. When it passes through one polaroid, its intensity got half. Then Malu's law start uh, showing its effect. So first, an unpolarized light with an intensity of I naught at 16 watt per meter square is incident on a pair of polar lasers. The first polarizer has its transmission axis aligned at 50 degrees from the vertical. The second polarizer has its transmission axis aligned at 20 degrees from the vertical. So basically this is unpolarized light. So first the polaroid is like this. Sorry, it should be like this, more of a like this. So here it is 16 watt per meter square. After this it would be half 8 watt per meter square as it is unpolarized. Then its transmission axis aligned at 20 degree from the vertical. So here it is 50 degrees. So now light is at 50 degree angle and going to the 20 degree. So theta is 50 degree minus 20 degree. So here we will get 8 into cos square 30 degree. So that would be 8 into 3 by 4, which is 6 watt per meter square, and that is your answer. But now if linearly polarized beam of light with an intensity of 16 watt per meter square is incident on the same pair of polarizer and the polarization direction of the incident light is 20 degree from the vertical what is the intensity of light emerging from first polarizer and the second polarizer. So light is at 20 degree, then P, which is a polarizer, is like 50 degree. So the angle between draw it like this. So then it will become this. Then again here it is 20 degree. So then the light will become like this. This is 20 degree. Okay, this is 16 watt per meter square. So the theta here will be 50 degree minus 20 degree, 30 degree. So this would be 16 cos square 30 degree, which is 16 into 3 by 4, which is 12. Then here also theta is 20 degree minus 50 degree, which is 30 degree. So here it will be 12 cos square 30, which is 12 into 3 by 4, this is 9. See, here we get 9 watt per meter square, but if we start with the unpolarized light, we will get at 6 watt per meter square. So always remember the thing whether it is a polarized light or unpolarized light which is going through the first polarity. Now we solve the quiz question of the previous year quiz of this course, which is the week 3 quiz question of this course previous year. So a wave suffers refraction at interference separating two media of refractive indices N1 and N2. The property of the wave that remains unchanged is, here I have discussed the property, which property remains unchanged, that is V by lambda 1, which is actually frequency mu by F. So basically I am telling you again and again that we are discussing things in the domain of optics where no new frequency is generated. So that would be answer frequency. Now go on to the next question, that is for a wave propagation in an isotropic. See here, this thing is mentioned, isotropic and homogeneous medium. When you get to know the polarization better, you will see the reference medium and all those things, where they are not neither isotropic nor homogeneous. The plane of vibration of the wave constants, we have seen that this contains both electric field and propagation vector, and this has also been written in the slides of the class. Okay. So the next question is, if the two waves represented by two waves are represented as E1 2 sine omega t plus pi by 2 and 3 sine omega t plus pi by 2, if these two waves are superimposed, the phase of a resultant wave. So the phase of a resultant wave became, okay, what we are discussing. So the phase actually is alpha, right? That is alpha. So here you can see that the initial phases are the same and their frequency is also the same. So the phase of the resultant wave will be the same, pi by 2, which is this. So this is pi by 2. Here is the question, is the two light waves overlap in the space, the resultant would be. So here they are at pi, they are out of phase, basically the angle between them is pi. So we know that if the angle is pi or the odd multiple of the pi, we'll get a linearly polarized light, but it will be like in this direction. Then the superposition of left circularly polarized and right circularly polarized waves of same amplitude results in. So always remember that if we superimpose, this is RCP, and on top of that we superimpose LCP. So they will cancel each other like the pi by 2 phase difference. So basically, even we consider that left circular polarized is pi by 2 ahead and right circular polarized is pi by 2 behind, so their difference became pi. So when there is pi phase difference, we will get the plane polarized wave. See, then the next question, two waves are superposed in space with some phase difference. Phi. The phase difference is phi. The maximum amplitude of resultant wave for the phase difference phi will be. So we know the resultant is resultant wave E01 whole square plus E0 2 whole square plus 2E01 E02 cos alpha 2 minus alpha 1. This is phase difference. So we need this term to survive. It only survives or this term maximum. So we need the maximum value of cos. Cos maximum value is 1. So when we get cos theta is equal to 1, when theta is 0. So this is actually 5. So 5 needs to be 0. That's how you solve. This is basically not a like optics question. If you know this equation and you know the mathematics, you know the answer. Then this is the resultant of two constitutive waves having equal amplitude with relative phase difference pi by 2 plus 2m pi will be, we know what it would be. It would be less circularly polarized, and this is pi by 2 plus 2m pi. Huygens theory predicts that the speed of light traveling from denser to rarer medium will remain the speed of light. So we know sin I by sin R here. R is V1 by V2. V2 if the light is traveling from denser to rarer medium, so I will be less and R will be greater. So sin I is less than sin R. So V1 is less than V2. So V2 will be greater. So the answer is greater than the denser medium. And that is the correct relation between the phase difference and path difference. We have seen that delta is equal to 2 pi by lambda optical path difference. Even if it's not optical path difference, if it is not optical path difference, we can slide it as the 2 pi by lambda into path difference. So path difference will be lambda by 2 pi into phase difference. Only this. Here only this option has lambda by 2 pi, not 2 pi by lambda. So that would be the actual thing. Then question 10, which is basically two light waves, 2E0 sine kz minus omega plus pi by 2 and overlap in space. So here you see that A is not equal to B. Okay, but they had a phase difference pi by 2. So that will not be a circularly polarized light. So this will become definitely an elliptically polarized light, but linearly polarized light is also an elliptically polarized light. If you like see the thing that if omega t becomes 0, that kz omega t minus 0 sin pi by 2 at kz minus omega t is equal to 0. The first point would be 2e0 ex 2e0 and 0. and when kz minus omega t becomes pi by 2, and it becomes minus pi by 2, you get E0 is 0 and Ey is minus 0. Here, then kz minus omega t is equal to plus pi by 2, then sin pi is always is 0, and that would be E0. So this is going to be an elliptically polarized light. So this is for today, and um, we will discuss module 4 in the next week.